A matrix is a rectangular arrangement of numbers in rows and columns. The dimensions of a matrix are talking about how many rows there are versus how many columns there are. So we say the dimension is with m rows and n columns. And we write this as an m by n. It looks like a time sign, but we read it m by n. And in the example up here, we have 5 rows, 1, 2, 3, 4, 5, and we have 5 columns. And it's hard to see the dimensions with this one because they're the same, but we would call it nonetheless a 5 by 5 matrix. Elements are defined as the numbers in a matrix. This example below shows the elements in the matrix. You have the elements 4, 0, -1, 6, 5, and 3. And we talk about certain positions of numbers or elements in the matrix by their row and their column. So the number 5 here is the element in the first row and the third column. The element in the second row, second column would be 6. And what if I asked you what element was in the second row, first column? What would you say? Second row, first column. That would be a 0. And now just to go back to the dimension definition, we always start with rows versus columns. So we have 2 rows and 3 columns, and we would name this a 2 by 3 matrix. All right, we need to talk about equality of a matrix. Matrices are considered equal if their dimensions are the same and the elements in the corresponding positions are equal. So I'll say it again. Matrices are equal if their dimensions are the same and the elements in the corresponding positions are equal. And here's the typed out definition of that. So let's talk about adding and subtracting matrices. We will look at this key concept down here, and I'll get rid of that. And it says to add or subtract two matrices, simply add or subtract elements that are in corresponding positions. And it's important to note in the highlighting that you can add or subtract matrices only if they have the same dimensions. So let's look at adding matrices. Here you have two matrices and they're using algebra just to represent the elements. And if I wanted to add the first row, first column A number to the first row, first column of the second matrix, you would just end up adding A plus E, and they wrote it out long way here. Subtraction is the same, but be careful with that minus sign. Remember, first row, first column would be A minus E, and then you'd move over to first row, second column, that would be B minus F, and those are written out the long way here. So let's go ahead and do an example, and you'll see this is pretty straightforward. So here we have two matrices that I'm attempting to add, and it's always best to write down the dimensions to make sure they're the same. And since we're new with dimensions, we'll do this for the first two examples. Example A has 2 rows and 2 columns, and so we would write that this is a 2 by 2 matrix. Example, or the second half of the example, is also a 2 by 2 matrix. If you ever had it where the matrices were not equal, you would just say no solution. But these are equal, and so we can add them. And so I will take the number 3, first row, first column, and add that to the first row, first column over there. And I'll write it the long way the first time, just for your notes, but eventually you can skip this middle step. So you're really taking 3 plus a -1. And maybe I should write it like that to be particular. So we have 3 plus a -1, and that will give us the element in the first row, first column. Then we do first row, second column, plus the first row, second column, and leave a little space, and that will be 0 plus 4. And close your brackets. Moving down to the second row, I have second row, first column, plus second row, first column. So that would be a -5 plus 2. And here I have, finally, the second row, second column, plus second row, second column. And that will be -1 plus 0. And then you just go ahead and do the addition and get your new elements of your matrix. So 3 plus a negative 1 is 2, 0 plus 4 is 4, negative 5 plus 2 is a negative 3, and negative 1 plus 0 is 0. And you should also notice that the dimensions of your answer matrix match the dimensions of your original matrix. We'll move right on and we'll do the second example B. Do a quick check and make sure they're the same dimensions. This is 3 rows by 2 columns, and this is 3 rows by 2 columns, so we certainly can add them together. And in between, my step is to take 7 minus a negative 2, 7 minus a negative 2, and then in my first row, second column, I'll get 4 minus 5. And get that set up. Then in my second row, I'll have 0 minus 3, and my second column is negative 2 minus a negative 10, and then finally a negative 1 minus a negative 3, and 6 minus 1. And then when you go ahead and add these all up, you will get 7 plus 2, which is 9, 4 minus 5, which is negative 1, 0 minus 3, negative 2 plus 10 is 8, negative 1 plus 3 is 2, and 6 minus 1 is 5.
Alright, here are 2 guided practice problems. Pause the video now and do them and come back and check your answers with mine. Alright, here are the answers to the matrix. Remember, you can use a calculator for these, no big deal. Alright, we're going to move on now and talk about a scalar and then move on to talking about multiplying a matrix by a scalar. A matrix in algebra is a real number, and that's all it basically is. And so let's write down this definition. In matrix algebra, a real number is often called a scalar. So scalar multiplication is multiplying each element in the matrix by whatever scalar you have. So you multiply each element in the matrix by the scalar. So let's move down here to our examples and see what a scalar looks like. Here you have a scalar, negative 2, outside the matrix. This is multiplication. And all you do to solve these problems is take that negative 2 times every single element inside there and come up with your answer matrix. So negative 2 times 4 is a negative 8. Negative 2 times a negative 1 is a positive 2. 2 times negative 1, I'm sorry, negative 2 times 1 is a negative 2. 0, negative 4, and negative 14. So once again, all I'm doing is multiplying this number times each one of these elements. Here's an example that combines multiplication with addition. And just like the order of operations, you're going to multiply before you add. So you'll have to write a few steps here. First step is to take that 4 and multiply it by every element inside that matrix. And you end up with negative 8, negative 32, 20, and 0. And then you would go ahead and add that second matrix to it to get your answer matrix. I guess I'll just rewrite that down to be complete. And so you end up with negative 8 plus a negative 3, which is a negative 11. Negative 32 plus 8 is a negative 24. Whoops. Coming. 24. Whoop. And then 20 plus 6 is 26, and 0 minus 5 then, or 0 plus a negative 5 would be negative 5. So again, make sure you're multiplying before you do addition or subtraction. Okay, well that idea of the order of operations brings us to the properties of matrices, and so I'll explain these to you a little bit. Just like you had associative properties of multiplication and addition, you also have properties with matrix operations. And so here are 4 of them. Capital A and capital B and capital C are all big matrices. We don't know the dimensions, but they're the same. And then K will represent a scalar, which is just a number. And so you have an associative property of addition for matrix operations, meaning if you have three matrices and they're all being added, you can group them however you'd like. You could group the first two matrices and add them and then add the third, or you could group the last two and then add the first to it. Commutative property of addition means A plus B, matrix A plus matrix B, will yield you the same answer as matrix B plus matrix A. The distribution property of addition, that works with the scalar. So this is your scalar number outside, just a number, times matrix A or B will give you the same answer as if you took the scalar times matrix A and added to it the scalar times matrix B. And then you have the distributive property of subtraction, which is the same thing basically, except you have subtraction there. So matrices are so important because what they do is they take ginormous chunks of data and allow you to do a large number of operations on that data relatively quickly. So let's move on and use some of these properties. So we're going to do this example that is a multi-step problem involving manufacturing, and I'll read it. It says a company manufactures small and large steel DVD racks with wooden bases. Each size of rack is available in 3 types of wood: walnut, pine, and cherry. Sales of the racks for last month and this month are shown below. So here you have your small racks, and here you have your large racks, walnut, pine, and cherry in both columns. And then your sales for those racks last month and this month for each type of wood. So we're going to organize this data as they tell us to, using 2 matrices, one for last month's sales and one's for this month's sales. So I will just write that down. Last month and this month. And this one takes a little space, so leave yourself some room. Okay. And then I'm going to compare, let's see, I'll put walnut here, and pine, and cherry. I'm going to make matrices out of this information. And then I'm going to look, my first column will represent the small cabinet, and my second will represent the large cabinet. And then I have to do that for this month too. Small cabinet and large cabinet. So let's go ahead and construct our matrices. And we look at the information above. And last month, for a small walnut cabinet, we sold 125 of those. So go ahead and put that in as your first element in the first row, first column. Then we look over and we get walnut large last month. So here's walnut, well, we got to go over to the large. Walnut large last month was 100. So that'll be my number in my first row, second column. And go ahead and fill in your numbers: 278, 251, 225 for cherry small last month, and cherry large last month was 270. And we are looking for the average, I believe. Write and interpret a matrix giving the average monthly sales. So I'm just writing my matrices right now, and then we'll decide how to find the average in a little bit. So now I'm moving over to this month, which will be all my bottom numbers. And for a small walnut, it was 95 that were sold. A small, I'll stick in the small column, small pine was 316. And a small cherry was 205. And here these numbers are in the other large rack sales column. And we get that. Now again, the question is, write and interpret a matrix giving the average monthly sales for the 2-month period. Well, how do you find the average? It's a typical average. You have to add up the numbers and divide them by 2. So I will write this up here, that I'm going to take 1/2 after I add up my numbers in matrix A plus matrix B. So there's 2 ways of doing this. This is now turned into distributive property. I could first add up my numbers inside there, and then take it in half, which I think I'm going to do, but you could also do the distributive property and take half of A right away and half of B right away and then add them together. But I'll do it the first way I said, where I add A and B first. So I'll put my 1/2 outside and leave it there for now, and rewrite my matrices that I had. And I'll pause while I do this. I'm just going to rewrite the blue matrices. Okay, and I told you to take a lot of room, so I had to squish it over. But there are my two matrices that were in blue, and now I'm just putting them together in a mathematical statement. And now I will add them together. I'll carry down the 1/2. And my new matrix, when I add the elements in the same row, same column, 125 plus 95 gives me 220. And then I would get 594, 430. When I add first row, second column, I'm going to get 214. That's coming from 100 plus 114, 466, and 570. And now I'm close to being done. I just need to multiply through that 1/2 in my answer matrix, which I will write in red so it stands out. Would be 110, that's half of 220. 594 divided by 2 is 297. 215 over here would be 107. Second row, second column is 233, and third row, second column is 285. So there you can see how order of operations and all the properties came together in this nice problem. This example is one that you commonly see, but kids somehow don't hear the end of the lesson or they ignore this, but you're going to see this problem a lot on quizzes and tests. And here we're using a matrix to solve the equation for x and y. So if you look embedded into the matrices, you have your x value, and there you have a y value. They're quite straightforward to answer. You just have to set them up the right way. And so what we're going to do is use our order of operations, and I'm going to add these two matrices together first, then I'll multiply by 3, and then you'll see quite straightforward how we get x and y out of that. So let's add together our two matrices first. I'll put the scalar 3 on the outside. And I'm just going to write down 5x plus 3 for my element in the first column. I took 5x and I'm adding 3 to it, but that's the most I can simplify it right now. Then I will take that negative 2 plus 7, which is just a 5 over here. Moving down, I'm going to do 6 plus a negative 5, and that's just 1. And then finally, I'm going to do negative 4 plus a negative y. And there's nothing more I can do with that except write negative 4 minus y. And close off my brackets. And I don't really need those parentheses anymore, but I don't think I can erase them, so I'll put them back. All right? Those are really unnecessary parentheses, but they're stuck there now. So now I'm going to go through and I'm going to multiply all that stuff by 3. And you will see that when I multiply the 3 times this, it turns into a distributive property problem. So I would do 3 times 5 and get 15x, and 3 times 3 and get 9. That's just my first row, first column element. Then move on and do 3 times 5 and get 15. That's my first row, second column element. And moving down to the second row, I do 3 times 1, which is 3. And then finally, another distribution property. I will have to take this 3 times a negative 4, which gives me a negative 12 minus 3y when you distribute that. So this is a matrix. I'm going to put the brackets around it. And now, in order to solve for y, this is the important part. Write that answer matrix over here, and you'll see that you end up with some equations. You know that this first row, first column element has to equal that one if these are truly equal matrices. And so we just write that separately somewhere and do the work. That we know that 15x plus 9 must equal a negative 21. Okay? And so we just go ahead and solve it. And when you do that, you're going to end up with x equals negative 2. Likewise, for the y, you know that this element must equal that element. And so you know negative 12 minus 3y must equal a negative 24. And solve that with algebra and end up with y being 4. So you have to do a little work to get there, but it's nothing that you can't handle. All right, here's another example, and I really encourage you to do this because you see this problem everywhere. I want you to solve this matrix for x and there's the y. Solve it for x and y and come back and see if you get the right answer. All right, I didn't show the work, but I do know the answers. I know that x must equal 5, and I know that y is going to equal 6. So if you need help in getting that, come find me and I'd be happy to help you.